Sasekhona la ebamba ilanga secondary school, senior secondary school, bamba ilanga libamba lichisa. Molo bhuti kunjani?
Phela khona njani bhuti?
Akhonto mana khonto andikhali.
Andikhali nami bhuti.
Kuhleke. Why isikole senu sibizwa ngebamba ilanga? I mean mina ngiyagodola la kuyabanda. There's a lot of wind, you're high up in the mountains. What's behind the name?
This isikole ligama lebamba ilanga ligama lenkosi ligama lenkosi.
Oh, inkosi ubamba ilanga. All right, praise be to His Royal Highness. All right, Brawamike, yini mbuzo wako for our teacher in the studio namhlanje?
My question say, what happens inside galvanic cell?
Well, thanks for that question. Let's just repeat it for our viewers at home. They specifically asked what happens inside a galvanic cell. Now, if you can remember from last week's lesson, we started to take a look at your electrochemical reactions. And those means that your electrochemistry specifically, which means it was the transformation between electrical energy and chemical energy. Now, we've taken a look at two cells, which was the first one last week, electrolytic cells, but today's discussion is then going to be on galvanic cells. Now, just to take you back again to your electrolytic cells from last week, let's just take a look at what happened again. Remembering that we've got, in this case, a specific beaker with two electrodes placed inside of it, and these electrodes are connected to a cell or otherwise just a power source. Now we've made use of sodium chloride, which we would like to break up. So when I ever have sodium chloride inside a solution, it is going to dissociate into sodium ions, which is positively charged, and chloride ions that was negatively charged. And then because the one electrode was connected to the positive of the battery, it made it being positive, and the other one was connected to the negative, making it negative. And therefore, at the end of the day, we had the electrolysis process taking place where the positive went to the negative electrode and the negative went to the positive electrode. Okay, but that was now for your electrolytic cell. Let's move on to your galvanic cell. You would notice that your galvanic cell is going to look a whole lot different than your electrolytic cell. In your galvanic cell, we're going to have two beakers now. And on each side, we're going to have one electrode being placed into these beakers. You would also note that we do not have a cell or a battery at the top anymore. We've just got connecting wires connected to a voltmeter that will then measure any specific electrical current. Connected though to these two beakers, you've got this glass tube, which is going to be what we're calling the salt bridge. Now later on we'll tell you all about what the salt bridge does and what the functions is, but for now let's just take a look at an example to explain how a galvanic cell actually works like. Now in our example, we're going to be making use of a zinc electrode placed inside a zinc sulfate solution and a copper electrode that's going to be placed inside a copper sulfate solution. Now do take note that these sulfate ions are just going to be spectators. They're not going to take part in the reaction itself. It will just be the zinc ions, the copper and the copper ions. Okay, now you'll notice that inside my salt bridge, we've got what we call a salt. Obviously because it's a salt bridge. The only difference is it's not necessarily table salt. We all know that table salt is NaCl, but this salt can be any metal that is positively charged and any non-metal that will be negatively charged. So in this case, we're using sodium nitrate as our salt for our salt bridge. Okay, now we're going to need to be making use of a redox table as well to explain what two half reactions is going to occur inside my galvanic cell. Now once again, you would have noted that I did not add the whole redox table for you. There's just not enough space on my slide, but I've placed your specific reactions in the most important order, remembering that we are using the 4B table that usually starts with lithium at the top. Okay, so here's my zinc and my zinc ions that we found in the solution, as well as the copper ions and the copper. Now what's important to note here is we are working with a galvanic cell. This is going to be a spontaneous reaction, and that means my oxidation half reaction must be above my reduction half reaction. Now taking a look, I've got two half reactions. It's going to be zinc and copper. The one at the top must be the oxidation in our case because it needs to be spontaneous. So therefore, my zinc is going to act as the oxidation half reaction. My copper will then act as the reduction. But because it's oxidation, we always read it from the right-hand side going towards the left. And because it's reduction, we read it from the left-hand side going towards my right. So we notice that we'll form zinc ions and we'll form copper metal. during this reaction. Okay, so let's go back to our cell and see what happens. That means that my zinc rod that you find placed inside the zinc sulfate solution is going to be the one that's going to give off electrons. Now these electrons are going to be traveling along this piece of external wire towards the copper side, and then when it gives off these electrons, it's going to form Zn2+ ions that goes into the solution. On the other hand, the copper is going to be attracted to these negative electrodes that's coming from the zinc side, and this copper ion is then going to be plated onto this specific copper metal rod. So that means during this reaction that my zinc ions is going to be losing electrons and thus become lighter, or in this case corrodes away, so it's going to become thinner and thinner, and on the other side my copper electrode though is going to be gaining copper and therefore will become thicker and heavier as time goes along. Okay, now let's go and write on our two half reactions. We already know that zinc is going to be the oxidation half reaction, so we're just going to copy and paste from the right hand side going towards your left hand side, and remembering that your copper is going to start on your left hand side and then we're going to read it towards the right hand side. Now in order for us to be able to write on an overall reaction, we must make sure that the electrons completely cancel out. And these electrons can only cross-cancel each other out. That means something from the left-hand side can cancel something from the right-hand side. And luckily in this case, that will be the case. My zinc, with just 2 electrons, is going to completely cancel out with my copper on the left-hand side. And now we'll just add everything on the left and on the right-hand side. So we end up having zinc plus copper ions, and that ends up giving us zinc ions, as we've seen, as well as copper metal. Okay, now we also need to take a look at now what's the function of the salt bridge inside of this galvanic cell. As we've noted, zinc is going to form zinc ions inside the cell, and that's going to make this whole cell become more positively charged. On the other hand, seeing that we're removing the positive copper ions out of the solution, we will now be left with only negative ions inside the solution, and thus it will make this side of the cell more negative. Now, in order for this cell to continue operating, we're going to need to make sure that there's electrical neutrality. So there should not be an excess positive and negative charges. And this is where the salt bridge comes in. Our salt bridge contains positive ions and it contains negative ions. So that means my positive sodium ion in this case will be traveling through the salt bridge towards my solution that has, now in this case, too many negative ions. And on the other hand, the negative ion will then travel through our salt bridge towards the beaker that has got too many positive ions. Okay, so that means that my salt bridge completes the circuit. It is also going to allow electrical neutrality and lastly facilitate the movement of ions. And when we are referring to ions, we are referring to your salt bridge ions, the sodium ions and the nitrate ions in this specific case. Okay, now let's take a look at some characteristics of my galvanic cells. In this case, it's going to be chemical energy converted into electrical energy. So it is now the opposite of your electrolytic cells, and it's actually going to act like a battery. Because if you buy a battery, you have chemicals inside the battery that is going to bring about, in this case, an electrical energy being given off. And that's then what we can make use of to power any of our apparatus. Okay, now also this is a spontaneous reaction, as I've mentioned earlier, which means that oxidation is above reduction on my redox table. So remember that we said oxidation must be above reduction. Also, there's going to be 2 solutions, and they're going to need to be separated by a salt bridge, and they always will end up having a positive cell potential. If you can remember last week, we spoke about those positive and negative cell potentials. And lastly, oxidation will always occur at the anode, but in this case it will be the negative electrode, and reduction occurs at the cathode, which in this case will now be the positive electrode. Now once again, people, we are briefly touching on this section.
Phila khona kunjani ku? Mina ngifresh. Uba igama lakho ngaphi?
Khatshala Thembakazi apha eBeach eMthatha.
eBeach.
eBeach.
Spell it?
Bityi. Beach.
All right, here at Butai in Umthatha. All right. Uthini umbuzo wakho for Tisha wethu estudio.
How do I represent my reaction using cell notation?
Well, thanks for that question. Let's just repeat it again for our viewers at home. I ask, how do I represent the reaction using cell notation? Okay, now what's important to note is, although we've got both electrolytic cells and galvanic cells, only galvanic cells are able to have a cell notation. You won't have that for electrolytic cells. Okay, now let's go and take a look at the general template of your cell notation. You would take note though that there is a few backslashes, but there's a specific double backslash in between. Now this is going to indicate to us our salt bridge. So all that this really represents is basically your two beakers with the salt bridge in between. Now, whenever you have your first beaker, the first one will only indicate for you the oxidation half reaction, and that must always be the case. And remember that oxidation occurs at the anode. The second beaker will contain whatever happened at the cathode, and you know that that would then be the reduction half reaction. Okay, and then you will notice there's also a few backslashes in between these specific beakers, which is the anode or the cathode. Now, these backslashes actually indicate to you the phase change. Now, remember that when we talk about a phase change, we are referring to whether it was something like in a solid or liquid or in a gas, or more specifically also in aqueous solutions when we take a look at our phase changes. Now, what I'm going to make use of is a specific example to help us understand this a bit better. Now, luckily, we've already seen this in our first part of the lesson, where we had zinc that ended up forming zinc ions, and we had copper ions that formed copper. So we know that zinc, because it shows that it loses electrons, will undergo, in this case, oxidation. And remember that that means for us it's going to occur at the anode, the very first part. And the copper ions, though, is going to be gaining electrons to form copper metal. Thus, this is going to be reduction, and that's going to be happening at the cathode, which is in the second beaker in our cell notation. Okay, but now we also need to take into consideration these three standard conditions under which this cell must operate. And you unfortunately would need to know these three standard conditions off by heart with these specific quantities. The first one is temperature. Temperature will either be at 25 degrees Celsius, or unless you want to use the Kelvin scale, you can say 298 Kelvin. Then the concentration of the electrolyte solution, that must be at 1 mole per cubic decimeter. And the last standard condition is pressure, which you can either state as 1 atmosphere, or you can use 101.3 kilopascals as your quantity there. Okay, so that means that our reaction of previously is going to be needing to work under those three standard conditions. Okay, so let's go back to our template and see if we can now add in what happened during our reaction. Let me just take you back quickly to that reaction again. We had our zinc forming zinc ions, and then we had copper ions forming copper. So, starting off at our anode, we're going to have zinc, and we're going to have it forming zinc ions. Now remember that zinc all by itself will be in the solid phase, whereas your zinc ions is going to be in the aqueous phase. On the other hand, we're going to have copper ions, which is going to be in the aqueous phase. That's going to be forming copper, which will be in the solid phase. Now, what's important to note though here is whenever you've got an aqueous phase, you're going to need to show the concentration of the electrolyte solution. So next to it, unfortunately, I don't have enough space for next to it, you're going to write 1 mole per cubic decimeter, as well as in your copper ions case, 1 mole per cubic decimeter. Great, so I hope that's going to help you. And remember, it only goes for galvanic cells, not for electrolytic cells.
Keleza nathi.